Step outside on a clear night. Find somewhere away from the sodium haze of the city and give your eyes time to adjust. 10 minutes if you can manage it. 15 is better. The sky changes when you stop forcing it to perform on command. At first, it offers you the obvious things. The brighter stars, the familiar patterns, maybe a planet if one happens to be up. But then the fainter structure begins to come through. The darkness develops texture. The black stops being flat. And somewhere in that texture, if the air is clear and the sky is dark enough, you'll notice something that isn't quite a star. A faint oval blur, soft-edged, not bright, not dramatic. It looks almost accidental, like a fingerprint left on the glass of the sky. That blur is the Andromeda Galaxy. Most people who know the name know it in a very general way. It is the galaxy next door. It is far away. It is large. It will one day collide with the Milky Way. Those statements are true as far as they go, but they leave out the thing that matters most, which is scale felt from the inside. They give you the label without the weight. And the weight is the whole point, because if you actually sit with Andromeda, not just as an astronomy fact, but as a physical object existing in the same universe as your body and your breath and the ground under your feet, something interesting happens. The words you normally use start to lose their sharpness. Big becomes too casual. Far becomes almost meaningless. Even galaxy, a word we throw around comfortably now, begins to recover some of its original force. Over the next couple of hours, that is what we're going to do. We're going to recover the force of the thing. We're going to move slowly enough for the numbers to stop behaving like trivia and start behaving like reality. We're going to trace how humans first noticed Andromeda, how we learned what it was, how large it really is, how much of it we can see and how much we cannot, what lies at its centre, what its history appears to have been, what its future may be, and why this particular neighbouring galaxy matters so much to our understanding of the wider universe. There is no need to rush. In a way, rushing would miss the point. Objects like this are useful precisely because they force the mind to slow down. Human intuition evolved for distances measured in steps and fields and horizons. Even our largest practical scales, cities, countries, oceans, remain small enough to be absorbed by the body without much strain. Space is different. Space requires reconstruction. To think clearly about it, you have to build new instincts one careful layer at a time. So let us begin with the simplest fact. Andromeda is visible to the naked eye. You do not need a telescope to know that another galaxy exists. You need darkness, patience, and a little guidance. But no machine is required. That alone is a remarkable sentence. Another galaxy, visible with the unaided eye. What your eye is catching, when it catches that small patch of light, is not a nearby cloud, not a local disturbance, not some faint ornament on the ceiling of the sky. It is the combined light of an immense system of stars, dust, gas, stellar remnants, star clusters, dark matter, and one central black hole, all bound together by gravity and drifting through the universe as a single coherent structure. It is a system so large that if you tried to cross only the visible part of it at the speed of light, the trip would take longer than all of recorded human history many times over. And yet it appears as a smudge. That contrast between appearance and reality is one of the reasons Andromeda is such a powerful object to think with. It reminds you that reality is under no obligation to feel proportional to itself. Some of the largest things you will ever know can enter your life quietly. They can arrive dimly, almost apologetically, with none of the spectacle you might expect. Understanding then becomes a kind of correction. Not a change in the object, but a change in you. So this is where we start, with the dim thing in the dark, and with the suspicion that it is more than it appears to be. History begins there as well. There is also a particular advantage in beginning with the naked eye rather than with a telescope or a data set. It keeps the story honest. Before there were observatories, before spectral lines, before distance ladders and orbital solutions, there was simply a human being under the sky, noticing that one patch of darkness was not quite dark. Science never fully leaves that origin behind. Even at its most technical, it is still an elaboration of attention. Andromeda is a perfect object for remembering this, because no matter how advanced the science becomes, it remains accessible at the level of first encounter. It is still something you can point to with a finger. The first known written description of Andromeda comes from the year 964. A Persian astronomer named Abd al-Rahman al-Sufi included it in his book of fixed stars and described it as a small cloud. That phrase survives because it is so modest and so exact. A small cloud. It does not claim too much. It does not pretend to know more than observation allowed. It simply records what a careful eye found. There is something admirable in that restraint. Human beings often prefer dramatic errors to humble uncertainties. We like grand explanations. We like the feeling of completion. But astronomy, at its best, is built on the discipline of not lying to yourself about what you can actually see. Al-Sufi saw a cloud-like patch and called it a cloud-like patch. He did not know he was looking at another galaxy. No one could have known that then. The tools did not yet exist. The conceptual framework did not exist either. For centuries, Andromeda remained exactly that kind of object. Known, but not understood. The telescope improved the situation only gradually. When European astronomers began turning early telescopes toward the heavens in the 17th century, the planets changed shape, the moon became a landscape, Jupiter acquired moons of its own, and the sky in general began to lose its old simplicity. But Andromeda was stubborn. It did not resolve into a crisp thing. It stayed diffuse. Simon Marius, observing it in 1612, compared it to a candle shining through horn, a soft, filtered glow without hard boundaries. That image tells you something important about the pre-modern view of the universe. Objects were classified first by appearance. Stars were points. Planets wandered. Nebulae were clouds. The sky was a place of categories inferred from light, and if the light remained vague, the category remained vague too. Andromeda spent a long time in the category of nebula, which simply meant a blurry celestial object. It was not yet understood as a star system because individual stars could not yet be separated out from the whole. Even in the 18th and 19th centuries, when astronomy became more systematic, Andromeda was still filed under names like the Great Andromeda Nebula. Charles Messier catalogued it as M31. William Herschel and others studied nebulae extensively, but the true nature of these objects remained uncertain. Some were clearly gas clouds within the Milky Way, others were more mysterious. Were all nebulae local? Were some unresolved star clusters? Were some something else entirely? This uncertainty mattered because it sat at the boundary of a much larger question. How big is the universe? If the Milky Way contained everything, then nebulae had to belong to it somehow. If they did not, then our cosmic address was far less central than many astronomers had assumed. The difficulty was that Andromeda did not offer an answer easily. Through better and better instruments, it continued to appear both structured and unresolved. By the 19th century, observers could trace a brighter core and an elongated outer haze. Spiral form was suspected in some nebulae, and photography began revealing shapes the eye alone missed. But shape is not distance. You can guess at what a thing might be from how it looks. You cannot prove it. Andromeda was a problem suspended between appearance and interpretation. There is a broader lesson here, and it runs through much of science. Discovery is often delayed not by a lack of intelligence, but by a lack of conceptual permission. Human beings can look directly at something for generations and still fail to understand it because the framework needed to interpret it has not yet crystallized. Another galaxy can hang over your species for 1,000 years and still remain a cloud if the thought another galaxy is even possible has not become available. That thought, once it arrived, would be revolutionary. But before it could arrive fully, astronomy had to pass through a period of argument. It had to become comfortable with the possibility that the universe might be much larger than the best current map suggested. That is a difficult transition in any field. Large corrections are never only technical, they are psychological. They require people to let go of the world that made them feel oriented. Andromeda became the instrument of that letting go. Not immediately and not by itself, but decisively. It sat there through centuries of incomplete interpretation, waiting for optics, measurement, and theory to catch up. It did not change. Our ability to read it did. That is one of the more sobering aspects of astronomical history. The heavens do not reveal themselves according to human urgency. They wait. The question is whether our methods become subtle enough in time. If you like, you can think of those early observations as humanity learning to hold a question open. That is not a small skill. Civilizations often prefer certainty to accuracy, especially about the heavens. The sky invites mythology because it is both visible and unreachable. To record Andromeda honestly as a cloud, and to leave it there until stronger methods arrived, was a form of intellectual discipline. It gave later astronomy a starting point not distorted by overconfident invention. Sometimes the cleanest inheritance one generation can give. The next is an unanswered observation. By the early 20th century, astronomy had reached a particularly interesting kind of uncertainty. Telescopes were now powerful enough to reveal enormous detail. Photography had transformed observation. Spectroscopy had opened up entirely new ways of reading light. And yet one of the biggest questions imaginable remained unsettled. Was the Milky Way the whole universe? Or was it only one system among many? It is hard, from the vantage point of the present, to fully recover how live this question was. We grow up inside the answer. Galaxies are familiar to us. School children learn the word casually. Images from Hubble and Webb have made the universe of many galaxies feel almost obvious. But obvious is often just another word for finished. In 1920, this issue was not finished. It was open. The disagreement became famous as the Great Debate, held in Washington, D.C., between Harlow Shapley and Heber Curtis. Shapley argued for an enormous Milky Way that effectively constituted the universe as a whole. Curtis argued that the spiral nebulae were independent star systems far beyond our own. Each man had evidence. Each also had blind spots. The debate was not a simple case of one person being rational and the other foolish. It was a genuine confrontation between two interpretations that the available data had not yet cleanly separated. Shapley had good reasons for believing the Milky Way was very large. His work on globular clusters had pushed the estimated size of our galaxy outward dramatically and displaced the Sun from the centre, already a profound humiliation for older geocentric instincts. Curtis, meanwhile, pointed to novae and spiral nebulae, and to their appearance as possible clues that these objects were not local clouds, but something much grander. The issue came down to calibration, distance, and the reliability of different lines of evidence. Andromeda sat directly in the middle of this dispute. If it was nearby, it could be treated as part of the Milky Way. If it was far away, then it was a separate galaxy, and the scale of the known universe would multiply almost overnight. There is a tendency to romanticize scientific revolutions as moments when a single crucial fact simply arrives and everything falls into place. Often the reality is messier. Evidence accumulates unevenly. Different methods point in different directions. Old assumptions persist because they still explain part of what is being seen. New assumptions seem extravagant until one measurement lands with enough force to make extravagance unavoidable. That is what happened with Andromeda. It was not merely that astronomers did not know the answer, they did not yet possess a sufficiently secure yardstick. Distance in astronomy is difficult because you cannot walk to the object. You cannot triangulate vast scales directly with ordinary means. You build a ladder. One method calibrates another. Nearby objects anchor more distant ones. Standard candles provide luminosity clues. Statistical methods and physical models constrain the possibilities. But if one rung of that ladder is uncertain, the uncertainty propagates. This is why the debate was so consequential. It was not just about whether certain cloudy patches were local or distant. It was about whether the methods available were mature enough to support an entirely new map of reality. A larger universe is easy to imagine poetically. It is much harder to prove numerically. The emotional tone of the period matters too. Astronomy in the early 20th century was becoming modern in a particularly intense way. It was no longer only positional astronomy, the careful charting of where things are. It was becoming astrophysics, the effort to understand what things are, how they work, how they evolve. That shift made old categories unstable. Nebulae could no longer remain merely descriptive. They had to be assigned physical identities. A blur was no longer just a blur, it was a problem. Andromeda was the most famous of those problems, partly because it was bright enough and large enough to attract sustained attention, and partly because it had just the right mixture of familiarity and resistance. It had been seen for centuries, catalogued, photographed, discussed, and still it had not yielded its distance conclusively. The object was right there, almost within reach conceptually, but not quite. When science is close to a transformation, the atmosphere around familiar objects changes. They become charged. Every new observation feels heavier than it did before, because everyone understands, even if only dimly, that some larger picture is about to break open. Andromeda in the 1920s was one of those charged objects. It had stopped being only a nebula and had become instead a test. The person who would settle that test was Edwin Hubble, though the settlement itself would rest on a much longer chain of work by others, especially Henrietta Swan Leavitt. Revolutions in science are often named after the person who delivers the decisive blow. They're rarely built by that person alone. What makes this episode especially interesting is that both sides of the debate were partly carrying forward earlier victories. Shapley represented the expansion of the Milky Way beyond older cramped models. Curtis represented the expansion of the universe beyond the Milky Way itself. Science often moves this way. One corrective insight hardens into a new limit, then a later corrective pushes through that limit in turn. No single stage is foolish. Each stage simply reaches the edge of what its evidence can comfortably support before the next stage begins to pry it open. Edwin Hubble's decisive work on Andromeda depended on a prior insight that had nothing to do with galaxies directly. It depended on the discovery that a certain kind of star could act as a distance marker. These were Cepheid variable stars, stars that brighten and dim in a regular cycle. Henrietta Swan Leavitt, studying Cepheids in the Magellanic Clouds, recognised a crucial relationship between their pulsation period and their intrinsic brightness. The longer the period, the more luminous the star. That relationship meant that if you measured the period of a Cepheid and compared its true brightness to the brightness observed from Earth, you could infer its distance. It turned a class of stars into a measuring tool. This was one of the great gifts astronomy has ever received, a way to read distance from rhythm. Hubble used the Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world, to examine Andromeda in unprecedented detail. Night after night he photographed the object, looking not merely for structure but for change. Eventually he identified variable stars within the Andromeda Nebula, among them Cepheids. That mattered because if these stars truly were Cepheids, then Andromeda could be placed on the distance ladder. He measured their periods, he ran the calculations. The result was astonishing. Andromeda was far too distant to belong to the Milky Way. Hubble's early estimate was lower than the best modern value, but that did not matter for the central conclusion. The object was outside our galaxy by a vast margin. It was an independent stellar system, another galaxy. It is difficult to overstate what that did to the human picture of the universe. One moment the Milky Way was plausibly the whole show. The next it was one island among others. Cosmology did not merely expand, it changed kind. The universe ceased to be a single city and became an archipelago. The phrase island universes, used earlier by some astronomers and philosophers, suddenly stopped sounding speculative and started sounding literal. If Andromeda was a galaxy, then the sky must contain many more such systems. Every spiral nebula became suspect in the best possible way. It might not be a local cloud. It might be an entire stellar civilization of matter, gravity and time, suspended unimaginably far away. Later measurements improved the distance. Today, the Andromeda Galaxy is generally placed at about 2.5 million light-years from Earth, more precisely around 2.537 million light-years in many references. That improvement reflects better calibration of Cepheids, other standard candle techniques, and a century of work refining the distance ladder. But again, the revolution does not depend on whether Hubble's first number was off by a factor of 2. The revolution lies in the category shift. Nearby cloud became external galaxy. This is one of those rare moments in intellectual history where a technical result carries a philosophical aftershock, immediately visible to almost everyone. The universe became larger, yes, but it also became less centred on us in a newly dramatic way. We had already lost centrality within the solar system and then within the Milky Way. Now, even the Milky Way itself was provincial. There is a temptation to tell this as a triumphalist story of science correcting human vanity, and there is some truth in that, but the better reading is gentler. What happened was not that humanity was humiliated by reality. It was that reality turned out to be more abundant than our earlier frameworks could hold. The loss of centrality came paired with a gain in richness. Andromeda was the first great neighbouring proof of that richness. Not the first galaxy to exist, obviously, and not even the first one people speculated about, but the first one measured with enough confidence to reorder the map. It became the nearest large spiral galaxy, the benchmark by which others would often be understood, and the external mirror in which astronomers could study the anatomy of a system, broadly like our own from the outside. That last point matters deeply. We live inside the Milky Way. That makes certain kinds of understanding hard. Imagine trying to learn the layout of a forest while standing in the middle of it with only a flashlight. You can study local trees well, you can infer patterns, but the whole shape is difficult to grasp. Andromeda gives us something like an exterior view of a large spiral galaxy, not identical to the Milky Way, but close enough to be instructive. So Hubble's result did two things at once. It multiplied the size of the known universe, and it provided astronomy with a neighbouring laboratory. Andromeda became not only a revelation about the cosmos at large, but a practical key to understanding our own galactic home. All of that flowed from careful measurements of stars that pulse. There is something beautiful in the economy of it. A question about the size of the universe answered by the heartbeat of a few distant suns. It is worth pausing too on the atmosphere of Mount Wilson itself. High on a mountain, using the greatest telescope of its day, Hubble was participating in a very old dream with very modern machinery to extend human sight until the universe could no longer hide behind blur. There is a romance to that, but also a discipline. Long exposures, patient comparison, careful identification, calibration against prior work. Discovery here was not sudden revelation so much as the reward for method. The universe expanded not because someone felt it should, but because a star pulsed and a measurement held. Before we can say how big Andromeda is, we need to rebuild intuition from the ground up. Space punishes lazy scale. If you move too quickly from ordinary human distance to galactic distance, the mind protects itself by turning everything into abstraction. Numbers stop landing. They become symbols of largeness rather than descriptions of reality. So begin close. Think of the room around you, a few meters across perhaps, maybe 10. The body understands this scale without effort. You know what it means to cross it, to reach to the wall, to walk from one end to the other. Even a kilometre remains within bodily imagination. You can picture the walk. You can feel time accumulating in your legs. Now expand. The moon is about 384,000 kilometres away. That is already beyond embodied intuition, but it still exists within the reach of story, because human beings have gone there. Apollo astronauts crossed that gulf in a few days. The number is large, but history has given it handles. The Sun is different. At roughly 150 million kilometers, it sits 1 astronomical unit away. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. When you see sunlight, you are seeing the Sun as it was 8 minutes ago. This is a manageable delay. It still fits in the imagination. You can make coffee in 8 minutes. You can wait through a traffic light in 8 minutes. The speed of light seems fast because it is, but the solar system is already large enough to make even light spend time in transit. Now go one step beyond the Sun to the nearest star system, Proxima Centauri in the Alpha Centauri system, roughly 4.24 light years away. Suddenly the units change because kilometers become unhelpful. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. It is not a measure of time, though it contains the word year. It is a measure of distance with time hidden inside it. Proxima Centauri is far enough away that if you emitted a beam of light today, it would arrive more than 4 years from now. If you travelled there at the speed of the fastest probes humanity has launched, the journey would take tens of thousands of years. Already the imagination is under strain. Now consider the Milky Way, the galaxy you're inside. Depending on how you define the disk and halo, its visible stellar disk is often given as roughly 100,000 light-years across, though some features extend farther, and the full dark matter halo reaches vastly beyond that. Think about what that means. If a beam of light started at one edge of the disk and travelled straight across, it would not finish the trip until 100,000 years had passed. Entire species rise and vanish in less time than light needs to cross a galaxy. The Milky Way contains on the order of hundreds of billions of stars. Estimates vary because faint stars are hard to count cleanly, and definitions differ. But something like 100 to 400 billion is a common range. If you counted one star every second without sleeping, without stopping, without error, counting through every birthday, every storm, every empire, every extinction, you would still be busy for thousands of years. Hold that carefully. Not just the number, but the structure it implies. A galaxy is not a decorative cluster of lights. It is a gravitational city of almost unimaginable scale. Andromeda is about 2.5 million light-years away. Put differently, the gap between us and Andromeda is roughly 25 times the diameter of the Milky Way's visible disk. If you lined up Milky Way's edge to edge like coins across a table, you would need about 25 of them to bridge the distance. And the light entering your eye when you look at Andromeda tonight has been travelling all that time, around 2.5 million years. It left before our species looked the way it does now. It left before cities, before agriculture, before writing, before myth in any recognisable form. It left while early human ancestors were still learning what kind of creature they were going to become. And yet here it is. This is one of the strangest aspects of astronomy. Distant objects are not merely far away in space. They're also arriving from earlier times. Looking outward is always, to some degree, looking backward. The farther away the object, the older the light. Andromeda is close enough in cosmological terms that we still see it as a neighbouring mature galaxy, not as a radically younger object from the deep past, but even so the delay is enormous by human standards. There's another subtle point worth keeping in mind. Distance in astronomy is rarely the distance to an object's front edge, back edge, centre, halo, or some other obvious physical boundary. It is often the distance to its central region or a characteristic average. That matters for Andromeda because the object itself is large on a galactic scale. The light from its near side and far side is not leaving at exactly the same distance from us. The difference is small compared with the total gap, but it exists. Even neighbouring galaxies are deep enough in space to have thickness as far as light travel is concerned. Once you let these scales in properly, Andromeda begins to change from a name into a situation. It is not just the next galaxy, It is a vast system suspended at a distance so great that the light we receive tonight began moving toward Earth before anything we would call civilization had even been conceived. That is the gap we're talking about when we talk about our nearest great galactic neighbour. Now we can ask the question in the title properly. How big is the Andromeda Galaxy really? The first answer usually given is that its visible stellar disk is roughly 220,000 light-years across. That is already enormous. It makes Andromeda about twice the diameter of the Milky Way's classic visible disk estimate, though modern comparisons can get slippery because both galaxies have extended structures, and because astronomers do not always mean the same thing by size. Are we measuring the bright optical disk, the radius at which the star density falls below some threshold, the gas disk, the stellar halo, the dark matter halo? Different answers produce different numbers. This is worth stressing because size in astronomy is not as simple as holding up a ruler to the edge of an object. Galaxies do not end with a clean surface. Their light tapers, their gas extends, their dark matter extends farther still. Their satellite systems and tidal debris complicate the picture. If you ask how big a city is, you have to decide whether you mean the downtown skyline, the municipal boundary, the suburbs, the commuting zone, or the broader metro area. Galaxies are like that, only less tidy. Still, the visible disk of Andromeda is a useful place to start. That disk contains the familiar spiral structure seen in photographs, the central bulge, the dust lanes, the broad, flattened stellar component, the regions of ongoing star formation. It is the part most people mean when they visualize the galaxy. And at about 220,000 light-years across, it is large enough to make the Milky Way feel less like a giant and more like one major example among several. But the visible disk is only the bright core of the problem. Surrounding that disk is an extended halo made of older stars, globular clusters, hot gas, and dark matter. The stellar halo is diffuse. The gaseous halo, often referred to as the circumgalactic medium, extends even farther and is difficult to detect directly because it is tenuous. The dark matter halo is inferred from gravitational effects and dominates the mass budget. Depending on which of these components you emphasize, the real Andromeda can become much larger than the luminous objects seen in a conventional image. One of the most striking findings of the last decade is just how extensive Andromeda's surrounding material may be. Studies of its halo have suggested structures that reach out hundreds of thousands of light-years and in some descriptions over 1 million light-years. NASA's discussions of Hubble observations have pointed to a giant halo around M31. And other work on its circumgalactic medium indicates a layered, enormous envelope of matter extending far beyond the visible galaxy. This leads to one of the most quietly unsettling facts about our relationship to Andromeda. The two galaxies may already be touching, in the only sense that really matters, gravitationally at the outskirts. The Milky Way has its own extended halo. Andromeda has a larger one. The centres are about 2.5 million light-years apart, but the outer influence zones of both galaxies are so vast that the space between them is not empty in any simple way. There may already be overlap in their most diffuse components. Two galaxies separated by millions of light-years, already in contact at the edges. That sentence feels wrong the first time you hear it because it violates a human habit of picturing separation as emptiness. But galaxies are not billiard balls. They are not hard objects moving through a vacuum with clean boundaries. They are nested distributions of matter and gravity. Their outskirts blur into the intergalactic environment. Their edges are thick with possibility and uncertainty. There is also the question of mass. Total mass estimates for Andromeda vary depending on method, but broadly speaking it appears to be of the same general order as the Milky Way, possibly somewhat more massive depending on which components and assumptions are included. Earlier popular accounts often spoke as though Andromeda were clearly much more massive than the Milky Way. More careful modern work has made the comparison more nuanced. In visible stars, Andromeda likely has the larger count. In total mass, the two may be more similar than once thought. This matters because it reminds us again that visible size and total gravitational heft are not identical. Andromeda's central bulge is also more prominent than the Milky Way's. It appears in some respects to be a more evolved, or at least differently evolved, spiral system, one shaped by a distinct history of mergers and star formation. So size is not just a matter of diameter, it includes the proportions of components: bulge to disk, gas content, star formation activity, halo richness, satellite environment. If you were close enough to Andromeda to see it with the sort of clarity you can see the Milky Way from inside, the impression would not simply be our galaxy, but larger. It would be its own thing, broader, more bulge-dominated, marked by long dark lanes of dust and a different record of interactions. So how big is Andromeda really? The honest answer is that the question has layers, about 220,000 light-years across if you mean the bright visible disk. Far larger if you include the surrounding halo, larger still, in a sense, if by size you mean the full reach of the galaxy's gravitational and gaseous environment. The image your eye catches as a smudge is only a fragment of that total. What you see directly is the concentrated central light. Most of Andromeda is too dim, too spread out, or too dark to register without instruments. The galaxy is not lying to you. Your eyes are simply optimized for other problems. This mismatch between the visible and the real is one of the central themes of modern astronomy. The universe is rarely exhausted by appearance. In Andromeda's case, the object in the sky is already extraordinary. The object behind the appearance is larger still. There is a useful mental habit here. Whenever you hear a galaxy's size quoted as a single number, silently ask, which part? The answer might be perfectly valid, but it is never the whole object. Optical disks reward the eye, halos reward patience, gas rewards multi-wavelength observation, dark matter rewards inference. A mature picture of Andromeda has to hold all four at once. Once you do, the title question starts to sound slightly mischievous. How big is Andromeda really? Big in light, bigger in gas, bigger still in gravity. The word really turns out to hide several different, equally physical meanings. Andromeda contains roughly 1 trillion stars. That number is so large that it risks becoming decorative. Trillion is one of those words that modern life has cheapened slightly through overuse. Economies use it, governments use it, technology companies use it, news cycles spend it casually. But a trillion stars is not the same kind of trillion as $1 trillion. Money is symbolic, stars are physical. They have mass, temperature, chemistry, lifetimes. They bend space-time. They throw off stellar wind. They host planetary systems. They explode. They leave remnants. They alter one another. 1 trillion stars is not just a count. It is 1 trillion centres of consequence. Even the estimate itself deserves a moment. No one has stood outside Andromeda counting stars one by one. Stellar population estimates are built from luminosity functions, mass models, resolved star counts in accessible regions, and extrapolations guided by what we know about stellar evolution. Hubble's recent large mosaic of Andromeda resolved on the order of 200 million stars, which is astonishing in itself, but that is still only the bright fraction visible to the telescope in that survey. NASA's 2025 release emphasised that those 200 million individually resolved stars sit inside a galaxy whose total stellar population is estimated around 1 trillion. In other words, even when you photograph Andromeda with a space telescope over more than a decade, across more than 600 pointings and billions of pixels, you're still only scratching the luminous surface. Try to let the number be physical. 1 trillion stars means 1 trillion gravitational wells where gas collapsed under its own weight, heated, ignited, and entered the long economy of nuclear burning. Some of those stars are small, cool red dwarfs that will outlive the current age of the universe. Some are stars like the Sun. Some are blue giants that blaze hard and die young. Many exist in binaries or larger multiple systems. Some are isolated. Some orbit in quiet suburbs of the disk. Some crowd together near the bulge where stellar densities rise, and the night sky from any hypothetical planet would be unlike anything we know. Around many of them there are almost certainly planets. We cannot catalogue Andromeda's exoplanets individually with current methods. It is far too distant for the techniques used in the Milky Way to work at that scale. But we do not need a direct census to make the broader inference. Exoplanet studies in our own galaxy strongly suggest that planets are not rare exceptions. They are a normal outcome of star formation. There are rocky planets, gas giants, ice worlds, mini-Neptunes, super-Earths, and likely countless bodies that do not fit our current taxonomies neatly. So when you say Andromeda contains 1 trillion stars, you're almost certainly also implying an immense population of worlds, a number so large that ordinary language becomes clumsy. There are probably planets there that have never known darkness because they orbit in bright multiple star systems. Planets with no star at all, ejected long ago into the cold interstellar medium. Worlds forming right now in dusty disks around young stars in active star-forming regions. Worlds that froze before Earth existed. Worlds that may possess chemistry every bit as rich as ours. Worlds that may host nothing more than sterile rock and wind. Worlds where, statistically speaking, some interesting things might eventually happen. The question of life changes in emotional texture when you scale up properly. At small numbers it feels speculative. At large enough numbers it begins to feel like a question about repetition under broad conditions. That is not the same as saying life must exist elsewhere in Andromeda. We do not know that. But the scale shifts the burden of feeling. It becomes harder to think of Earth as the only place worth considering, simply because the stage is so extravagantly large. There is another way to approach the number. If you started counting Andromeda's stars 1 per second at the moment anatomically modern humans first appeared, you would still not be done, you would not be close. Even if you had been counting continuously for 300,000 years, never sleeping, never losing your place, you would only be partway through. This kind of thought experiment is useful not because it yields new scientific information, but because it restores friction to large numbers. The mind needs friction. Without it, the phrase 1 trillion stars becomes a polished surface off which awareness simply slides. Andromeda's stellar population also tells a story about its past. The mixture of star ages, metallicities, distributions and motions is not random. It preserves evidence of how the galaxy formed and what happened to it afterward. A large bulge of older stars, a disk with younger populations, streams and halos carrying remnants of disrupted satellites, clusters fossilized from earlier epochs. All of it turns the galaxy into an archive. 1 trillion stars are not just simultaneous lights, they are a layered record of time. This is one reason nearby galaxies matter so much. In distant galaxies we often see integrated light, broad structure, gross statistics. In Andromeda we can resolve stars individually in many regions and ask more detailed questions. Which stars are young? Which are metal-rich? Which belong to the thin disk, the thick disk, the bulge, the halo, the streams? Which populations were likely born in Andromeda and which were accreted from smaller galaxies later absorbed? 1 trillion stars, then, is not just a statement of immensity. It is a statement that the object is both populous and knowable in layers, dense enough to overwhelm ordinary intuition, close enough to study in detail. That combination is rare. It is part of what makes Andromeda invaluable. When people call it the next galaxy over, they are technically right. But the phrase understates the case almost comically. The next galaxy over contains 1 trillion stars. The neighbour is not small. What kind of galaxy is Andromeda, structurally speaking? The usual answer is that it is a spiral galaxy, specifically a large spiral viewed at an angle of about 77 degrees relative to our line of sight. That tilt is important because it shapes almost everything about how the galaxy appears to us. We do not see Andromeda face on, where the spiral pattern would present itself as a broad pinwheel, nor do we see it fully edge on as a thin line. We see it obliquely, which is why photographs show an elongated bright oval with dark dust lanes and an intense central concentration of older yellowish stars. The central bulge is prominent. More prominent, in fact, than the Milky Way's bulge appears to be in proportion to its disk. This has encouraged astronomers to think of Andromeda as a galaxy, with a somewhat different evolutionary path from our own. Its bulge is dense and dominated by older stars. The surrounding disk contains the dust, gas, and younger stellar populations associated with spiral structure. Farther out, ring-like and arm-like features host sites of active star formation, including well-known regions such as NGC 206, a massive star cloud visible in images. Spiral arms themselves require a little care in how they are imagined. A naive image is of fixed bright strands of stars physically winding around the centre, like paint on a spinning record. The more accurate picture is subtler. Spiral structure is often described in terms of density waves, or pattern structures through which stars and gas move. Gas entering these regions is compressed, making star formation more likely. Bright young stars then illuminate the pattern. The arms are real, but they are not rigid filaments. They are dynamic, evolving features emerging from the physics of rotating disks. Andromeda's star formation rate appears lower than many people expect for a galaxy of its size. It is not inert. New stars do form there, but it is not presently in a spectacular starburst phase. In fact, some astronomers have described it as transitional in character. A spiral with a large old stellar component and a disk that is less vigorously active than a naive picture of a giant spiral might suggest. NASA's 2025 Hubble released quoted researchers comparing Andromeda to a train wreck in the sense that its recent history seems unusually disturbed, with evidence for past interaction and bursts of star formation followed by relative decline. That phrase should not be taken to mean the galaxy is falling apart. It is more that its present condition looks historically consequential. Something happened, or, more accurately, several things happened over time. The galaxy we see now appears shaped by interactions significant enough to leave visible marks in its stellar populations and large-scale structure. The disk contains dark dust lanes that are especially striking in photographs because of the viewing angle. Dust in galaxies is often easiest to appreciate not when it glows, but when it blocks. Against the luminous inner disk and bulge, Andromeda's dust shows up as broad shadowed arcs and filaments. These are cold reservoirs of heavier elements and molecules, the byproducts of previous generations of stars and the raw material out of which future generations can form. Dust is a reminder that galaxies are not just arrangements of stars. They are ecological systems in which stars are born from gas, manufacture heavier elements, die, and enrich the medium from which new stars and planets later emerge. Andromeda also has a rich system of globular clusters, dense spherical concentrations of old stars orbiting in the halo. These clusters are among the oldest stellar systems associated with a galaxy, and serve as valuable traces of its formation history. Some likely formed early within Andromeda itself. Others may have been acquired when smaller galaxies were tidally shredded and absorbed. Cluster systems are a kind of galactic archaeology kit. They preserve motion, chemistry, and age in ways that help reconstruct the past. Then there are the satellite galaxies. The two most famous visible companions are M32 and M110. M32 is compact, bright, and peculiar enough that astronomers have long suspected it may be the stripped remnant of a once larger galaxy that ventured too close to Andromeda. M110 is a dwarf elliptical companion with its own interesting properties. Beyond these well-known satellites lies a larger population of dwarf companions distributed through Andromeda's broader halo. These small galaxies are not merely ornaments. They are participants in Andromeda's history and future, sources of past mergers, future accretion, and dynamical complexity. The question of whether Andromeda has a bar structure in its inner regions, like many barred spiral galaxies, has also been studied extensively. Because of the viewing angle and the complexity of the bulge, the bar is not as visually obvious as in some face-on spirals, but models and observations suggest that bar-like internal structure may well be present. If so, it would help channel gas and influence stellar orbits in the inner disk, adding another layer to the galaxy's dynamics. All of this is to say that calling Andromeda a spiral galaxy is accurate but incomplete, in the way calling Earth a rocky planet is accurate but incomplete. The label gives you the broad category, not the lived detail. Andromeda is a spiral galaxy with a large bulge, a tilted disk, active but not overwhelming star formation, heavy dust structure, an extended halo, many globular clusters, several notable companions, and strong signs of a complex interaction history. In other words, it is not just a shape, it is an arrangement of processes. A galaxy is not like a sculpture that has already finished becoming itself. It is a long-lived event. Andromeda is therefore useful not only because it resembles the Milky Way in broad outline, but because it differs from it in revealing ways. Comparative anatomy works in galaxies as it does in biology. A neighbouring spiral with a larger bulge, different star formation history, stronger visible signs of interaction, and a somewhat different satellite population gives us a second case study, close enough for real detail. The Milky Way alone would always leave us wondering which of its traits are generic and which are peculiar. Andromeda gives us a nearby answer sheet with many of the same questions filled in differently. If you watch a galaxy only with your eyes, you learn almost nothing about its mass. Light tells you where some of the matter is, what kinds of stars dominate the view, where dust is blocking radiation, and how the overall structure presents itself. But light alone does not tell you how the galaxy behaves dynamically. For that, you need motion. Here is the simple expectation. If most of a galaxy's mass were concentrated in the bright central regions, then stars and gas farther out in the disk should orbit more slowly, much the way planets farther from the Sun move more slowly than planets close in. That is the familiar Keplerian intuition. Once you get beyond the bulk of the mass, orbital speed should decline. But when astronomers measured the rotation curves of galaxies, including Andromeda, they found something else. The outer regions were not slowing down the way visible matter alone predicted. They remained too fast. The rotation curve stayed unexpectedly flat. That discrepancy forced a choice. Either our understanding of gravity was radically wrong on galactic scales, or galaxies contain substantial mass we cannot see directly. The second possibility became the dominant explanation, and remains one of the major pillars of the dark matter framework. Andromeda's rotation curve was an early and important case in this story. Its outer stars and gas move in ways that imply a huge gravitational reservoir beyond the luminous disk. Not just a little extra matter tucked between the stars, but an enormous halo of invisible mass. This is what astronomers mean when they say a galaxy lives inside a dark matter halo. The stars are embedded in something larger, something that shapes the whole system while refusing to emit or absorb light in ordinary ways. Dark matter is one of those subjects that easily slips into mystique, partly because it sounds speculative, and partly because the name itself is so open-ended. But in the galactic context, the idea is not decorative. It is a sober response to motion. Something is there. If it were not, the observed orbits would not make sense. That does not mean every detail is settled. The exact distribution of Andromeda's dark matter, the precise total mass of the halo, the relation of that halo to the Milky Ways, and the broader particle nature of dark matter remain active areas of research. But the underlying inference is solid. The visible galaxy is only the luminous skin of a much larger gravitational object. This changes what it means to picture Andromeda. Most people imagine the galaxy as the thing in photographs. The golden bulge, the dark dust lanes, the blue-white outer structures. Those are real, but they are not the whole body. In some sense, they are only the glowing embroidery on a much larger invisible garment. The true Andromeda, as gravity experiences it, includes a huge dark scaffold within which the visible stars move. There is an almost philosophical discomfort here. Human beings trust what shines. We are visual creatures. we instinctively grant reality to what produces an image. Modern astrophysics keeps teaching us that this instinct is incomplete. The universe is not built only from what is optically generous. Much of its structure hides in dynamics, in X-rays, in radio emission, in absorption features, in lensing effects, in motions whose meaning must be inferred. Seeing in astronomy often means assembling many kinds of evidence until something invisible becomes undeniable. Andromeda is useful because it makes this lesson concrete. You can begin with the naked eye smudge, then you move to telescopic structure, then to stellar populations, dust maps, gas distributions, proper motions, spectroscopic velocities, halo studies, and dynamical modelling. With each step, the object grows. It becomes less purely visual and more physically complete. Dark matter is not the only invisible component involved. The gaseous halo around Andromeda also matters. Hot diffuse gas can extend far beyond the bright disk, and observations in ultraviolet and X-ray regimes, along with absorption line studies using background sources, help trace that material. The circumgalactic medium acts as a reservoir, a recycling zone, and a record of inflow and outflow processes. Galaxies are not isolated from their environments. They breathe in a way, accreting gas, ejecting gas through feedback, interacting with satellites, exchanging matter with their halos. Andromeda's dark matter halo and gaseous envelope together mean that the galaxy's true physical presence in space is far more extensive than the visible photograph suggests. The photograph is a good beginning. It's not a complete ontology. This matters when people ask whether the Milky Way and Andromeda are already interacting. If you mean have their bright stellar disks collided, no. If you mean are there stars passing through one another, certainly not yet. But if you mean do their extended halos and gaseous environments already participate in a shared dynamical theatre, then the answer becomes more subtle. The scene is already set. The galaxies are already feeling one another as large gravitational systems embedded in a common local environment. So when we speak of the size of Andromeda, we should not stop at its visible light. A galaxy is not merely the part that glows, it is the whole structure required to keep the glowing part moving the way it does. For a listener trying to picture this, the easiest mistake is to imagine dark matter as a shadowy version of ordinary stuff. Hidden stars, cold dust, dim planets. That possibility was considered in various forms, but it does not get us far enough. The amount and distribution required are too large, and multiple independent lines of evidence across cosmology point beyond simply unlit normal matter. So when Andromeda's motion suggests a huge invisible component, it is not just telling us that our telescopes are missing a few faint objects. It is telling us that the galaxy is embedded in something more fundamental than ordinary luminous structure can account for. At the centre of Andromeda there is a black hole. That sentence is now familiar enough that it risks losing impact, but it should not. A black hole at the centre of a galaxy means that in the crowded inner region, amid ancient stars and complex orbital structure, there sits an object so dense that escape speed exceeds the speed of light. Not because it is actively devouring everything nearby like a cosmic vacuum cleaner. Popular culture has done a great deal of damage to black holes in that respect, but because gravity in that local region has become extraordinarily concentrated. The black hole in Andromeda is usually referred to as M31. Its mass is commonly given in the rough range of 100 to 200 million solar masses, substantially larger than Sagittarius A, the black hole at the centre of the Milky Way, which is about 4 million solar masses. This means the central engine of our neighbouring galaxy is not just larger than ours, it is larger by a factor big enough to change the emotional scale of the comparison. The galaxies may be neighbours. Their central black holes are not peers. Andromeda's nucleus is especially interesting because it appears double. High-resolution observations revealed two brightness peaks close together near the centre, often labelled P1 and P2. At first glance, that seems to suggest two nuclei, which is already strange enough to invite all kinds of speculation. but the currently favoured interpretation is subtler and in some ways more satisfying. One peak marks the true centre more closely associated with the black hole, while the other arises from stars moving in an eccentric disk whose orbits cause them to bunch up at one part of the path, creating an apparent secondary concentration. In other words, the nucleus looks double, not because the galaxy has two equal hearts, but because gravity has arranged stars into a shape that produces that illusion. This is a good example of how galactic centres resist simplistic pictures. We often imagine them as clean hubs, one bright core, one black hole, concentric symmetry. Real centres are more chaotic, more historical, more interesting. They preserve the memory of mergers, orbital resonances, gas inflow, star formation episodes, and the accumulated consequences of extreme density over enormous timescales. Andromeda's central bulge is dominated by older stars, giving the inner galaxy its warm yellow glow in many images. That older population says something about time. The bulge is not where you go primarily to look for the galaxy's newest stellar generation. It is where you go to study what has endured. These stars there orbit in a gravitational environment very different from the quieter suburbs of the disk. Densities are higher, velocities are more varied. The dynamical architecture is deeper, older, and more compressed. Black holes of this size also matter because they appear to correlate with properties of their host galaxies, especially bulge mass and stellar velocity dispersion. These correlations suggest that black hole growth and galactic growth are linked somehow, though the details remain a rich field of study. A galaxy does not merely happen to contain a central black hole unrelated to everything else. The black hole and the galaxy appear to co-evolve, influencing one another through feedback, accretion history, and structural development. That raises a broader question. Is Andromeda's large central black hole one sign of a more active or merger-rich past? Quite possibly. Galaxies grow through accretion not only of gas and stars, but in some cases through the merging of central black holes after galactic mergers. Each such event can reshape the nucleus. The current double structure may well reflect, indirectly, a long memory of interactions. And yet Andromeda's black hole is relatively quiet today by quasar standards. It is not blazing across the universe as an active galactic nucleus of the sort seen in distant young galaxies. It flickers at low levels, it emits modestly. It is not in a phase of furious feeding. That fact is itself interesting. Massive black holes do not need to be spectacular at every moment. Most of cosmic history is not spent in fireworks. Much of it is spent in simmering aftermath. From the standpoint of narration, it is tempting to turn the central black hole into the dramatic climax of the galaxy. But that would be misleading. The black hole matters immensely, especially for the inner dynamics, yet does not dominate the galaxy in the way a central sun dominates a planetary system. The stars in the disk do not orbit the black hole in any simple sense. They orbit the combined gravitational potential of the entire galaxy. The black hole is central, but it is not everything. What it does provide is a kind of conceptual anchor. The galaxy is not only broad and diffuse and beautifully spread out. At its heart there is also compression, extremity, and hidden violence. The same object that presents itself to the eye as a serene, luminous oval contains, at its centre, a darkness around which ancient stars move in complicated loops. That is one of the reasons Andromeda feels so satisfying to think about. It contains opposites without contradiction. Calm appearance and violent history. Diffuse outskirts and concentrated core. Trillion star scale and one black hole centre. It is simple enough to point at with the eye, and complex enough to occupy generations of astrophysics. At the centre of Andromeda there is a black hole. Around it there is a nucleus of strange geometry. Around that a bulge of older stars. Around that a disk of dust, gas and ongoing star formation. Around that a halo. Around that a larger environment still, and all of it remains one galaxy. There is something slightly perverse about how Andromeda looks from Earth. For an object so large and so important, it is surprisingly easy to underestimate visually. Its apparent extent on the sky is huge by deep sky standards. The full moon spans about half a degree. Andromeda's visible disk stretches roughly 3 degrees across the sky, about 6 moon diameters laid side by side. NASA's recent Hubble materials put it exactly that way, 6 times the apparent diameter of the full moon. If you could somehow see the entire bright structure at strong surface brightness, it would dominate a broad swath of the night. You would not need to be told where it was, it would command attention. But that is not what the eye experiences. The eye gets a central glow and perhaps, under good conditions, a hint of elongation. To many observers, the galaxy appears much smaller than it truly is, because most of its light is spread thinly over a large area. This is the crucial distinction between total brightness and surface brightness. An object may emit or reflect a great deal of light overall, and still appear faint if that light is diluted across enough sky. This is why Andromeda feels, on first sight, a little underwhelming to people raised on astrophotography. The long exposure image has taught them to expect luminous spiral arms, dark dust rivers, and a brilliant nucleus. The naked eye delivers something far subtler, a small haze, sometimes only barely visible. The disappointment is understandable, but it is also instructive. It shows how much of modern astronomical seeing is technologically mediated. Cameras accumulate photons your retina cannot hold. Processing stretches contrast. Telescopes increase resolution. The object itself has not betrayed you. Your eye is simply working under evolutionary constraints. There is a profound difference between knowing that Andromeda is 6 moon widths across and feeling what that means. Try this the next time you're under a dark sky. Hold your thumb out at arm's length and think about the moon. Then imagine 6 of them laid across the sky where Andromeda's disk would extend if your eye could gather enough light to register it clearly. The galaxy is not a point. It is an architecture spread across the heavens. This odd combination, large angular size, low surface brightness, helps explain why Andromeda could be visible to ancient observers and still remain mysterious for so long. It announces itself just enough to be catalogued, not enough to be understood. It offers presence without clarity. There is another sense in which Andromeda is visually large. It has become a kind of calibration object in human culture. Amateur astronomers use it to introduce people to the idea that they can look out and see another galaxy with their own eyes. Educators use it to bridge the gap between naked eye skywatching and cosmological thought. It is a threshold object, one of the few things that can shift a person from the local sky to the extragalactic universe without requiring them to leave direct experience entirely behind. That role is made stronger by the galaxy's tilt. Because Andromeda is seen nearly edge-on but not fully so, the dark lanes and long oval structure in photographs are visually legible in a way some face-on spirals are not. It looks like something flattened and grand, a disk presented almost as a profile. The geometry helps. It lets the imagination catch hold of the object more easily than if it were a perfectly circular haze. Modern images have radically deepened this visual relationship. The 2025 Hubble Mosaic, assembled from more than 600 observations over more than a decade, resolves roughly 200 million stars across a huge fraction of the galaxy. The final image stretches across about 2.5 billion pixels. When you zoom into it, the galaxy stops looking like a smooth object and begins to look granular. A sea of stars, dark dust lanes threaded across gold and blue, satellite companions hovering nearby, regions of recent star formation breaking the smoother flow of old populations. This matters because scale in astronomy is often easier to accept when it can be entered visually. A smooth glow still feels like a glow. A field of individually resolved stars begins to feel like population. The Hubble mosaic does something remarkable in that respect. It takes a neighbouring galaxy 2.5 million light-years away and lets you inspect it almost as though you were performing urban analysis from orbit. Not every star, of course, not even close, but enough stars to make the abstraction crack open. And yet even that image underrepresents the whole. It resolves around 200 million bright stars, while the galaxy likely contains around 1 trillion. Even our sharpest major portrait is both unprecedented and incomplete. That is the pattern with Andromeda. Every improvement in seeing reveals more, and every revelation comes paired with a reminder of how much remains beyond direct grasp. So there is a double lesson in how the galaxy appears. To the unaided eye, it teaches humility about perception. To modern instruments, it teaches humility about resolution. In both cases, the visible image is meaningful and insufficient at the same time. The object in the sky is large. The object in the data is larger. The object in reality is larger still. This is why dark sky observers often describe their first successful sighting of Andromeda with a particular kind of satisfaction. It is not the satisfaction of spectacle, it is the satisfaction of contact. You know you are not looking at the prettiest thing in the sky. You are looking at one of the most conceptually loaded things the unaided eye can ever see. The reward is not brightness, but context. A faint object becomes overwhelming only after the mind catches up. In that sense, Andromeda is almost the ideal astronomical teacher. It demands patience first and meaning second. Andromeda has a history, and like the history of most large galaxies, it is not peaceful. When we look at a mature galaxy from far away, especially one as visually graceful as Andromeda, the temptation is to imagine stability as its defining trait. The spiral structure suggests order. The broad halo suggests stillness. The bright bulge at the centre suggests permanence. But permanence in galaxies is usually only the slow expression of accumulated disturbance. Large galaxies grow by interaction, capture, disruption, and merger. Their elegance is often the final shape of many prior collisions. Evidence suggests that Andromeda has had a particularly eventful past. Its halo contains streams of stars, coherent substructures, disturbed populations, and signatures that point to earlier mergers with smaller galaxies. These are not merely decorative oddities, they are traces of meals. When a dwarf galaxy wanders too close to a much larger one, tidal forces stretch it, strip stars away, and eventually disperse much of its original identity into streams and shells. The stars survive, but the smaller galaxy as a coherent object may not. Galactic archaeology is the discipline devoted to reading these leftovers. By examining the chemistry, ages and orbits of stars, astronomers can identify populations that likely originated in different progenitors. A stream of stars with common motion and composition can tell you that a satellite galaxy was torn apart long ago. A disturbed outer disk or thickened halo can imply major interactions. Globular clusters themselves can arrive as immigrants, brought in by galaxies that no longer exist as separate entities. Andromeda appears to show signs of such accretion clearly enough that some researchers describe its recent past as more violent than that of the Milky Way. NASA's 2025 Hubble release quoted astronomers saying that Andromeda looks like it has gone through some kind of event that caused vigorous star formation and then a relative shutoff. A collision with another galaxy in the neighbourhood is one possible explanation. M32, one of Andromeda's compact satellites, is often discussed in this context. It may be the stripped core of a once larger galaxy that had a close encounter with M31, losing much of its outer structure in the process. Whether M32 itself was the main culprit in a larger disturbance remains debated, but the broader point stands. Andromeda is not a pristine spiral untouched by interaction. It is a system shaped by hierarchical growth. The same is true for the Milky Way, which has consumed smaller galaxies and continues to do so, but the evidence in Andromeda may point to a particularly consequential merger a few billion years ago. This matters for several reasons. First, It helps explain structural differences between Andromeda and the Milky Way. Andromeda's larger bulge, its streams, its somewhat lower present star formation relative to mass, and aspects of its outer disk all make more sense if it experienced a stronger recent interaction history. Second, it turns the galaxy into a laboratory for understanding what major spirals become after significant encounters. Spiral galaxies do not all age the same way. Their biographies diverge. There is a useful analogy here to geology. A mountain range is not just a shape. It is the visible outcome of tectonics, compression, uplift, erosion, and time. Likewise, a galaxy is not just a pattern of light. It is the visible outcome of inflow, merger, angular momentum redistribution, star formation, feedback, stripping, and orbital settling. To look at Andromeda well is to see not just what it is, but what happened. The Hubble mosaic is powerful partly because it supports exactly this kind of historical reading. By resolving stellar populations across vast regions of the disk, researchers can compare ages and compositions in ways that help distinguish between scenarios. Did star formations sweep across the disk in response to an encounter? Are certain regions chemically distinct enough to suggest accreted origin? Which substructures belong to the main disk and which are debris? These questions are difficult, but they are answerable in parts only because Andromeda is both large and nearby. There is also the larger cosmological point. In the prevailing picture of structure formation, galaxies build up over time hierarchically. Small structures form first and later combine into larger ones. A giant spiral like Andromeda is therefore not a single monolithic thing that condensed all at once and remained unchanged. It is a present arrangement assembled from many earlier arrangements. Some stars in Andromeda likely formed in systems that once had names of their own, if galaxies could be said to have names before they merged. This is one of the reasons big galaxies feel almost historical in a human sense. They are composites. They contain ancestry. The modern object includes the remains of previous objects, not as separate museum exhibits, but as living parts of the current whole. A stream in the halo is a memory still orbiting. A compact satellite may be a survivor with most of its body missing. A chemical anomaly in a stellar population can be the fossil of a different birthplace. Andromeda's beauty, then, is not the beauty of untouched order. It is the beauty of survival after repeated transformation. Its present calm has been earned through disturbance. Its structure is memory made gravitational. When people say galaxies get big by eating other galaxies, the phrasing is crude but not wrong. The universe builds by capture. Growth is cumulative and often violent. Andromeda is large in part because other smaller systems came too close and were unable to leave intact. Seen that way, Andromeda's history is not an exception. It is what large galaxies do. But because Andromeda is near enough to examine carefully, its scars are easier to read than most. It is both neighbour and archive. There is something almost biological about this if you step back far enough. Large galaxies metabolize surroundings. They draw in smaller companions, digest their structure, redistribute their stars, and grow more massive and more internally complex as a result. The metaphor is imperfect, of course, but useful. It reminds us that growth in the universe is rarely clean addition. It is transformation through incorporation. When Andromeda absorbs a smaller galaxy, it does not place it gently beside itself as an archive specimen. It unmakes the smaller system and remakes its contents as part of a larger order. Andromeda is moving toward us. That sentence has been repeated so often that it now sits in popular science almost like folklore, but its core remains true. Spectroscopic measurements show that the galaxy's overall motion relative to the Milky Way has a significant inward radial component. In simpler terms, the light from Andromeda is blue-shifted overall rather than red-shifted. Locally, gravity is winning over cosmic expansion. The local group is not being pulled apart the way vastly separated galaxy systems are. It is gravitationally bound, and its two dominant spirals are on an approach trajectory. The conventional long-term picture has been that the Milky Way and Andromeda will have a close encounter in roughly 4 to 5 billion years, followed by repeated passages and an eventual merger over a much longer span. Some recent simulations have complicated that certainty by suggesting the exact final outcome may be less predetermined than older textbook summaries implied. Depending on the masses involved, the influence of other local group members, and the details of transverse motion, a direct eventual merger might be somewhat less inevitable than popular accounts often suggest. But the broad truth remains that the two galaxies are dynamically entangled and headed toward a far more intimate future than they have now. This is usually described as a collision, which is accurate at the galactic level and misleading at the human level. The misleading part comes from the imagery the word collision evokes: smashing, shattering, explosion, impact in the ordinary sense. Galaxies are not like cars, they are mostly empty space. The distance between stars within a galaxy is vast. When two galaxies pass through one another, the probability of direct star-on-star collision is extraordinarily low. What collides primarily are gravitational systems, gas clouds, and orbital structures. The result is not a single moment of impact, but a long choreography of distortion. Tidal forces draw out tails and streams. Gas is compressed, sometimes triggering waves of star formation. Orbits are scrambled. Disks are heated and thickened. Spiral structure can be torn apart. The galaxies pass through each other, slow, swing back, interact again, and over time settle into a new configuration. The likely end state in the classical picture is a large elliptical or elliptical-like remnant, sometimes nicknamed Milkomeda or Milkdromeda. The organised thin disks would be gone. The resulting galaxy would be broader, smoother, more dominated by older stars, and dynamically different from either current spiral. The night sky, if anything like observers existed on Earth, or its descendants during intermediate stages, would be transformed over millions of years. Andromeda would grow larger, tidal distortions would appear, the Milky Way band would warp, the heavens would become strange in a way no human being has ever seen. And yet, for all this drama, the Sun would probably survive the merger in the straightforward sense. Our solar system is unlikely to suffer a direct stellar collision. It could be perturbed into a new orbit around the merged remnant. It could end up farther from the galactic centre than it is now. By the time this happens, the Sun itself will be nearing the end of its main sequence life, and Earth will long since have become a very different place. So the personal stakes are low, the conceptual stakes are not. Andromeda's approach matters because it reminds us that galaxies are not static decorations pinned to a fixed cosmic backdrop. They move, they influence one another. Their futures are open within the laws governing mass, motion, and time. The universe is not a museum, it is an active system of continuous rearrangement. It also forces another revision of scale. The object you can pick out as a smudge is not merely a neighbouring example of the kind of galaxy we live in. It is part of our future. Not metaphorically, dynamically. It is one of the principal external structures shaping the long-term fate of the Milky Way. There is something wonderfully unsettling about that. The eye identifies a faint patch. The mind, after enough work, realises it is looking at a participant in the future architecture of our galactic home. Andromeda and the Milky Way, together with dozens of smaller companions, form the local group, a gravitationally bound association spanning on the order of 10 million light-years. Beyond that lie larger structures, the Virgo cluster in the broader regional context, the supercluster scale, and the cosmic web itself with filaments, nodes, and voids stretching across hundreds of millions of light-years. Every time you zoom out, the pair shrinks in relative importance. The local group becomes one small neighbourhood among many. The supercluster becomes one strand in a much larger pattern. The observable universe, by current estimates, contains perhaps on the order of trillions of galaxies. And yet scale does not erase significance. Another galaxy existing among trillions would not matter to us in the same way if it were not the one we can see, study, compare ourselves against, and eventually interact with directly. Nearness grants intimacy. Andromeda is cosmically ordinary in some respects. A large spiral with a black hole, halo, merger history, satellites, and ongoing evolution. But ordinary things become extraordinary when they are close enough to examine properly. There is a familiar emotional ending to discussions like this, one that goes something like, "All this immensity should make you feel small." Maybe it should, sometimes. But small is not the only available response. Another is participation. The atoms in your body were forged by the same stellar processes that shape the stars of Andromeda. The carbon, oxygen, calcium and iron in you came from earlier generations of stars living and dying in galaxies. The physical laws organising Andromeda are the same laws organising your blood, your breath, your thoughts, your tools, your telescope, your image sensor, your equations. You're not outside the story looking in. You're inside it looking across. So the next time you go out under a dark sky, find the smudge if you can. Give your eyes time. Let the faint oval emerge, then hold the facts together at once. You're looking across roughly 2.5 million light years. You're seeing light that left before human civilization. You're looking at a galaxy with around 1 trillion stars, a vast halo, a large central black hole, a long history of mergers, and a future entangled with our own. You are seeing an object so large that its visible disk spans hundreds of thousands of light years, and its wider environment may already be brushing ours. And you are the part of the universe that has become able to know that. That, more than the size alone, may be the strangest fact in the whole story. Perhaps that is why Andromeda lingers so well in memory after you learn its facts. It is not only large, it is narratively complete. It has a visible presence, a historical discovery arc, a measurable distance, an internal anatomy, hidden mass, a scarred past, a central black hole, and a future relationship to us. Many astronomical objects are astonishing in one dimension. Andromeda is astonishing in almost every dimension at once. It is close enough to feel personal, and large enough to remain inexhaustible. Few objects can do both. So if the question is how big the Andromeda Galaxy really is, the best final answer may be that it is bigger than any single number can honestly capture, and more intimate than any distant object has a right to feel. It is a galaxy large enough that its outskirts blur into the medium between galaxies, old enough to contain the remains of many earlier systems, rich enough to hold around 1 trillion stars, and near enough that human beings with ordinary eyes can still find it from the surface of Earth. That combination is so improbable from the standpoint of experience that it almost feels staged for thought. But it is real. It is there. And tonight, if the sky is clear, it is waiting where it has always been. One useful way to feel the distance to Andromeda, without falling back on the same handful of large numbers, is to ask a more physical question. What would it actually take to get there? At the speed of light, the trip would take about 2.5 million years. That sentence is almost too familiar to be helpful, so translate it into something less polished. If a beam of light left Earth when the earliest ancestors of modern humans were still living in Africa, adapting to a changing landscape with stone tools and fire not yet securely in hand, it would only be arriving in Andromeda around now. Light itself, the fastest thing we know, the thing by which all other speeds are judged, needs geological patience to cross the gap. Now replace light with machinery. Voyager 1, one of the fastest long-lived spacecraft humanity has launched, is moving at roughly 17 kilometers per second relative to the Sun. New Horizons, famous for its Pluto flyby, also travels at extraordinary speed by human standards. But by galactic standards, these are barely motions at all. At such speeds, a journey to Andromeda would take not millions of years, but tens of billions of years, longer than the current age of the universe. A spacecraft launched by our civilization, using anything like our current technology, would not arrive there in any meaningful future. The Milky Way and Andromeda will likely merge before our hardware could bridge the distance under conventional propulsion. That matters because it restores some honesty to the idea of nearness. People call Andromeda our neighbouring galaxy, and it is. But neighbouring here does not mean reachable in the ordinary sense. It means nearby relative to the scale of galaxies. It means close enough that our instruments can resolve stars in it, close enough that gravity is already shaping the long future of both systems, close enough that it dominates the local group alongside the Milky Way. It does not mean a destination waiting just beyond the edge of current engineering. Suppose, though, that the impossible problem of travel were set aside, and you could somehow move toward Andromeda at a significant fraction of light speed. What would you see? For a surprisingly long time, not much would seem to change. Space is mostly emptiness, and large structures do not rush toward the eye the way mountains do on Earth. Even crossing the outer reaches between galaxies, you would not pass through a corridor of dramatic scenery. There would be long spans where the stars of the Milky Way slowly reconfigured behind you, where Andromeda gradually swelled ahead, where the black between them remained mostly black. The experience would be less like driving toward a city, and more like watching a continent rise from the horizon of time. And this is another place where human intuition needs correction. We often imagine travel through space as a sequence of landmarks, but on truly intergalactic scales there are almost none. There is no cosmic roadside, no sequence of stations, no natural rhythm of intermediate arrival. The emptiness is part of the fact. To travel toward another galaxy is not just to endure distance, it is to endure the absence of familiar forms of progress. Only much later, after immense time and distance have been spent, would Andromeda begin to present itself as a structure rather than a smudge. The central bulge would brighten, the disk would widen, dust lanes would become visually meaningful. Satellite galaxies such as M32 and M110 would separate themselves from the main body. Regions of star formation would begin to distinguish themselves from the broader yellow-white wash of older stars. Eventually, if you came close enough, the galaxy would stop looking like a single object at all and start looking like what it really is, an environment. That transition is worth lingering on. Galaxies are often pictured as things you look at from outside, full and complete, the way a cartographer might look at a map. But if you actually approach one closely enough, the object dissolves into conditions. You no longer see the galaxy. You see stars, gas, dust, magnetic fields, empty stretches, radiation, orbital paths, clusters, dark clouds, hot young associations, cold molecular reservoirs, and the background glow of a system too large to comprehend from a single position inside it. The Milky Way is like that for us already. We do not inhabit the idea of the Milky Way, we inhabit one particular location within it. And if a civilization ever inhabited a world in Andromeda, they would likely experience their home the same way. Not as a grand external spiral, but as a local sky slowly interpreted into a larger structure by science. This is one reason Andromeda matters so much in comparative astronomy. It allows us to study from outside the sort of system we ourselves live inside. It gives us the luxury of an exterior view. If we could actually go there, that luxury would disappear. We would trade one interior ignorance for another. The galaxy would become intimate but less visually total. Distance, then, does something paradoxical. It keeps Andromeda beyond physical reach, but it also preserves its shape for us as an object of thought. Too far to visit, close enough to study, distant enough to remain a whole, near enough to become specific. That is a rare combination. And it may be one reason the Andromeda Galaxy occupies such a durable place in human imagination. It is far enough to remain awe-inspiring, near enough to resist becoming abstract, and inaccessible enough to preserve a certain seriousness. It cannot be turned into a tourist fantasy without violence to the scale. It remains what it is, a neighbouring immensity. For all that we know about Andromeda, there is still a great deal we do not know. This is not a weakness in the story. It is one of the things that keeps the galaxy alive scientifically. A fully solved object becomes reference material. An unsolved one remains a frontier. Take dark matter. We know, in the sense that modern astrophysics uses the word know, that Andromeda behaves as though it sits inside a massive dark halo. Its rotation curve, halo dynamics, and the motions of satellites all point in that direction. But what dark matter actually is at the particle level remains unresolved. We can map its effects more confidently than we can name its substance. So part of Andromeda's size, part of its true mass, part of its gravitational identity still rests on a cosmic component whose underlying nature is open. Or consider the exact history of Andromeda's mergers. There is broad evidence that the galaxy has absorbed smaller companions and likely undergone at least one significant interaction in the relatively recent cosmic past. But the details are still being reconstructed. Which progenitors came in when? How large were they? What exactly happened to M32? Was there one especially transformative collision a few billion years ago, or several smaller but cumulatively important ones? How much of the present bulge and inner disturbance reflects mergers rather than secular evolution within the disk itself? These are not minor footnotes. They shape our understanding of how big spirals mature. There is also the question of star formation. Andromeda is still forming stars, but at a lower rate than many people would intuitively expect from such a massive spiral galaxy. Why exactly is its current star formation activity what it is? How much gas has been heated, redistributed, or consumed by prior events? What role did feedback from supernovae or the central black hole play in regulating the galaxy's internal ecology? How much of Andromeda's present calm is temporary, and how much is the sign of a long-term transition into a less active phase? Even the future is not perfectly settled. Popular accounts often say that the Milky Way and Andromeda will definitely merge. That may still be the most likely broad outcome, but precise simulations have shown that certainty is harder to claim than older simplifications suggested. Much depends on masses, transverse velocities, the influence of the triangulum galaxy, and the wider local group environment. The encounter is real, the approach is measurable, but the exact choreography, first passage, number of subsequent passes, merger timescale, final remnant shape, remains a matter of modelling rather than witnessed fact. And then there is the circumgalactic medium that diffuses a gaseous envelope extending far beyond the bright disk. We know it exists. We know it is extensive. We know it participates in inflow and outflow, in cooling, heating, and the exchange of matter between galaxy and environment. But the details remain difficult because diffuse gas is difficult by nature. It does not present itself in neat, luminous shapes. It has to be reconstructed through indirect signatures, absorption lines, high-energy observations, and careful theoretical work. This means that part of Andromeda's actual body, part of what makes it as large as it is, remains only partially charted. There is a deeper lesson in all this. Scientific knowledge is often strongest not where it eliminates mystery, but where it reshapes mystery into better questions. We are no longer asking whether Andromeda is a cloud in our own galaxy. That mystery has been resolved. We are now asking what kind of interactions built its current form, how its unseen mass is distributed, how its star formation history compares with the Milky Way's, and how exactly its future with us will unfold. The ignorance is narrower, more technical, and in many ways more interesting. This is part of what separates mature understanding from shallow wonder. Shallow wonder says only, how amazing. Mature wonder says, yes, and what precisely remains uncertain. The second kind of wonder does not diminish awe. It deepens it. It makes the object feel more real, because real things are rarely exhausted by a first description. Andromeda, then, is not just a known neighbouring galaxy. It is also an active problem. Its details are still being worked out. Its history is still being reconstructed. Its relationship to our galaxy is still being modelled with improving data. Its halo is still being mapped. its central region is still being interpreted. That continuing incompleteness is part of its value. It means the story is not over. It means astronomy is still in conversation with the object, not merely summarizing it. When people imagine science as a machine that eventually turns mysteries into dead facts, they miss this entirely. The best understood objects often generate the richest next layer of uncertainty. Andromeda is a perfect example. The more clearly we see it, the more specific our questions become. Clarity does not end the story. It upgrades it. So let us end where we began, with the smudge. Not because nothing more can be said, but because the smudge is still the most honest form of the encounter. Before the numbers, before the Hubble mosaic, before the dark matter halo, before the reconstructed mergers and the future collision and the trillion stars, there is still that first quiet fact, a faint blur visible in the dark. It is worth noticing how much can hide inside a blur. The Andromeda Galaxy is one of the best examples of this anywhere in astronomy. The eye catches almost nothing, and behind that, almost nothing, there is nearly everything that makes a galaxy. Stellar birth and death, dust chemistry, gas cycles, orbital structure, merger history, a central black hole, invisible mass, satellite systems, gravitational future. A faint patch of light becomes, under sustained attention, an entire world of structure. That transformation from smudge to system is also a small model of what science does more generally. It does not necessarily replace wonder with explanation. Often it makes wonder denser. It takes the blur and fills it with articulated reality. The object becomes more impressive not because it becomes more dramatic, but because it becomes more specific. And there is something deeply human in that process. We are a species that keeps trying to convert distant light into understanding. We take things that are almost too faint to register and build instruments, languages, and methods capable of giving them weight. We compare periods of variable stars. We model halo dynamics. We stitch together hundreds of telescope images into mosaics billions of pixels wide. We infer invisible matter from visible motion. We argue, revise, and begin again. All of that effort, when condensed into one line, sounds almost absurdly delicate. Another galaxy, understood from here, and yet that is what has happened. The next time you step outside and find Andromeda, it may still look exactly as it did before you knew any of this. A small haze, a soft mark on the dark. But your relationship to it will have changed. You will know that the apparent modesty is an illusion of distance in biology. You will know that the visible core is only the bright centre of a much larger structure. You will know that the light is ancient by human standards, that the object is both near and unreachable, that it contains 1 trillion stars and perhaps an even larger number of worlds, that it has survived collisions, that it is still changing, and that it is moving in relation to us even now. You will also know something slightly stranger, that understanding does not reduce beauty, it sharpens it. There is a version of astronomy that turns the sky into a catalogue, a set of names and measurements to be memorised and repeated. Names matter. Measurements matter. But the deeper reward arrives when those measurements become felt structure. When 2.5 million light-years stops being a recited phrase and becomes a kind of pressure on the imagination. When 220,000 light-years across stops sounding like a statistic and begins to feel like a challenge to what size even means. When a 6-moon-wide galaxy in the sky starts to feel less like an observational curiosity and more like a correction to the way vision itself handles reality. That is what Andromeda offers if you let it. Not just information but calibration. It recalibrates distance, it recalibrates size, it recalibrates what counts as nearby, it recalibrates what it means for something to be visible and still mostly hidden. It recalibrates what it means to live inside a galaxy while being able to study another one from the outside. It recalibrates the line between the ordinary and the extraordinary by showing how casually the two can coexist. A smudge in the sky, 1 trillion stars, a neighbouring galaxy, a future interaction partner, a historical archive, an unsolved scientific object, a lesson in perception, a lesson in scale. It is rare for one thing to be all of those at once. So if the question was whether the script could go a little farther, perhaps this is the place to stop. Not at the edge of information, but at the point where the information has had enough time to become atmospheric. Enough time to settle. Enough time for the mind to go back to that first faint blur and realise that it no longer looks empty. The galaxy has not changed. The sky has not changed. The only thing that has changed is the depth of what the smudge now contains, and that is more than enough reason to look up again